Okay, let's talk about series. And to talk about series, I'm going to need to continue a little bit about those subsequential limit type stuff. So I need to talk about lim_inf and lim soup, or the upper limit and lower limit of a sequence. So let's have a sequence. And we'll have E, like in the last video, be the set of all subsequential limits. Of that sequence Sn. We showed it was closed, and we showed that if you have a point in there, there is a sequence that converges to that. Okay, so let's have say alpha equal to the supremum of E. That value we're going to define to be the lim soup of the sequence S sub n as n goes to infinity. This is the upper limit of S sub n. Okay, and this always exists. Even if S sub n doesn't converge, I can always find the supremum of S sub n, or the lim soup of S sub n, the upper limit. And likewise, let's have beta equal the infimum of E, and that's going to be defined to be the lim_inf of S sub n, or the lower limit of S sub n. Okay, so these always exist. No matter if the sequence converges or not, it has an upper limit that exists and it has a lower limit that exists. If S sub n does converge, the upper limit and the lower limit are both the same, because E is composed of a single set. Every subsequence of a convergent sequence converges to the same point. So E only consists of one point. Alpha and beta would be equal to that value. And so the lim soup equal to the lim_inf tells you that the sequence actually converges. And so maybe that's a little proposition. And if you want to, you can sort of convince yourselves of that. I'm not going to prove it other than what I had just said. If the lim soup as n goes to infinity of S sub n equals the lim_inf as n goes to infinity of S sub n, let's say it's equal to L, then S sub n goes to L in the limit. Okay, and sort of vice versa. So that's kind of an if and only if. So let me do that if and only if there. So if the lim soup and the lim_inf are equal, the series converges. If the series itself converges, the lim soup and the lim_inf are equal to L. Okay, but if it doesn't converge, they still exist, and they still have some difference between them. So another little proposition: lim soup of S sub n is bigger than or equal to lim_inf of S sub n, and I'm not going to prove that. I mean, the supremum of a set is bigger than the infimum of a set, so that's basically all there is to it. I'll have you do some exercises on finding lim infs and lim soups, but that's all I want to say about it. We'll use it later when we're talking about convergence of power series, convergence of Taylor series, and how big of a radius of convergence things have. The lim soup and lim infs of the coefficients of those series are important. Okay. So what is a series? Okay, so let's let a sub n equals 1 to infinity be a sequence. We've got notation for adding up these terms. We'll call them terms if they're going to be part of a series. The notation sigma k equals n to m a sub k is equal to, that just says add up a sub n plus a sub n plus 1 plus dot 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 plus a sub m. M has to be bigger than n. If not, then this is an empty sum. But sort of conventionally, we never usually have m being less than n. If they're equal, then the sum is just the single point. Let's say kth partial sum. Let me say the nth partial sum of a sub k's is, it's the sum from k equals 1 up to n a sub k. So I add up the first n terms in the sequence, and that's the nth partial sum of the series. Okay. The sum, or the series, the sum from k equals 1 to infinity of a sub k says add them all up if I can, and what this really means is I'm taking the limit as n goes to infinity of these partial sums. Okay, so I can't actually add an infinite number of things together, but what I can do is I can take a limit as I add more and more of them, and the number of them that I add goes off to infinity. Okay. This is the series formed from a sub k. Okay, so our students often have a hard time differentiating between series and sequences. It's kind of a point. It's another one of those definitions that they're kind of vaguely mixed, because a series is a special type of sequence. It's a sequence of partial sums that form the series. And so a lot of times students have trouble differentiating when two things are the same, but one is a special type of the other. Like rectangles and squares. A square is a rectangle, but not all rectangles are squares. A series is a sequence, but not all sequences are series. It's another one of those type of definitions. Okay, so let's prove some things about series. So, first theorem. If the sum of a sub n from n equals 1 to infinity converges, then a sub n converges to 0 as a series, or sorry, as a sequence. Even I am kind of confusing them sometimes. So this sequence goes to 0, the sequence of the terms goes to 0 if the series formed from the terms converges. So let's prove this. So what I need to do is I need to let epsilon be bigger than 0, and I need to show that each of the a sub n's gets smaller than that epsilon, right? So I need to use the fact that the sum converges. So there is some in the natural numbers such that I'm going to say s minus s sub n is less than epsilon over 2, where s is the limit of the series and s sub n is the nth partial sum, and this is whenever n is bigger than capital N. Okay, so by definition a series converges if its partial sums converge to some limit. S is the limit that these partial sums converge to, so the difference between S and the partial sums gets small whenever I get far out in the sequence of partial sums. Alright, we're going to use epsilon over 2 because I need to use the triangle inequality to somehow get something about the individual a sub n's. So I'm going to take s sub n and s sub n plus 1 and take their difference. Okay, so then we want to show that a sub n minus 0 gets small. Well, this is equal to, let's go with a plus 1. This is equal to s sub n plus 1 minus s sub n, right? Which is equal to s sub n plus 1 minus s plus s minus s sub n, which is equal to absolute value of s sub n plus 1 minus s plus absolute value of s minus s sub n, which is less than epsilon over 2. Sorry, this is a less than or equal to by the triangle inequality. And this is less than epsilon over 2 plus epsilon over 2 whenever n is bigger than capital N. And that's equal to epsilon. So absolute value of a sub n plus 1 minus 0 is less than epsilon, i.e. a sub n goes to 0. And if a sub n plus 1 goes to 0, a sub n goes to 0. Alright. The converse is not necessarily true, right? The converse of this statement says if the things that I'm adding up get really small, then the series converges. That's not true. We'll see some examples of that later. Let me actually show you an example of it right now. So say 1 over n is equal to a sub n. Then the sum, well, then 1 over n goes to 0, but the sum of 1 over n from n equals 1 to infinity diverges. Let me show you why. So sum from n equals 1 to infinity of 1 over n is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. I'm going to write out a lot of these terms. I'm going to write out 16 of them. because at 16 I can sort of show the pattern of what's happening. I might have to slide over a little bit. That's a 13. And plus ... Okay. So this is bigger than or equal to 1. Well, say it's bigger than or equal to a half. And a half is bigger than or equal to a half. And a third is bigger than or equal to a fourth, so these two guys together are bigger than or equal to a half. Because I've got something bigger than a fourth plus a fourth, that's going to give me something bigger than or equal to a half. These four things together, bigger than an eighth, bigger than an eighth, bigger than an eighth, equal to an eighth. So four things bigger than 1/8 together would be bigger than or equal to a half. 8 things bigger than or equal to a 16th are bigger than or equal to a half. I can keep doing this indefinitely, so I'm adding up something bigger than a half plus something bigger than a half plus something bigger than a half. It's absolutely going to have to diverge, right? I can't keep up adding things bigger than a half and be bounded. So this series diverges as it's always 1/2 bigger after going to the next power of 2. Okay, and we'll see this in the future. This is a series convergence test that Cauchy came up with, and Cauchy did a lot of work with these series tests. We'll have a couple other things that we'll have to talk about that Cauchy did too. Okay. So let's say one more theorem here. So this theorem, if a sub n is positive, or non-negative actually, for all n, then the sum from n equals 1 to infinity, a sub n, converges if and only if the sequence of partial sums is a bounded sequence. Alright, so let's prove this. And I'm going to rely on the fact that we have the monotone convergence theorem. So if I had you guys prove that actually, that if you have a sequence, a monotonic bounded sequence converges, right? Or a sequence which is monotonic converges if and only if it's bounded. That's what we're going to get here. So because a sub n is non-negative, n equals 1 to k, a sub n is monotonically increasing, and so converges if and only if it is bounded. And that's the entire theorem right there. Okay. Alright. Let's call that good for this video, and then we'll hit some more series stuff in the next one too.